The new section is titled Dot Product and Matrix Multiplication. First thing we're going to talk about is what a row vector and a column vector is. A row vector just has a row, a single row. Row vector, or a row vector, it has one row. It is a 1 by n matrix. Rows, columns, one row. An example would be no commas on matrices, 2, 7, 3. This is a 1 by 3 row vector. It just has one row. One row that has 3 columns. Column 1, column 2, column 3. The columns are quite boring. They each have just one entry because there's only one row, but nonetheless it is a row vector. A column vector, I suspect you'll know what that is. It just has one, it's a matrix with one column. This is an n by 1 matrix. It just has one column. It has n rows, but only one column. 2, 3, 7 is the one column, and it has row 1, row 2, and there's row 3. It has 3 rows. It is a 3 by 1 matrix. If it just has one column, it is a column vector. 7, 0, 2 is a 3 by 1 column matrix. This matrix here, 2, 3, 1, 4, 9. This is it has one row but 5 columns. Column 1, column 2, column 3, column 4, column 5. This is a 1 by 5 column vector. It has one row, it's a column vector, it has one row, it is a row vector. If it has one column, it is a column vector. Can you think of a matrix that is both a column vector and a row vector? Well, to be a column vector, the number of columns better be 1. To be a row vector, the number of rows has to be 1. So to be both a column and a row vector, you have to have one row, one column. The matrix with one number in it. It has just one row and one column. This is both a column and row vector. It's a great test problem in my opinion. Give an example of a matrix that is both a column vector and a row vector. Okay. Nothing exciting here. Nothing exciting at all there. But it gets you to think, in my opinion. Okay. Now we're going to go on to a dot product. Let A equal A1, A2, up to AN, and B is equal to B1. Oops. B is to be a column matrix, column vector. And B is equal to B1, B2, up to Bn. So here's the dot product. A dot B. 3 lines means is defined to be A dot B, which is different. Well, okay. A dot B is defined to be A1 B1 plus A2 B2 plus A3 B3 all the way up to AN BN. You multiply the first entries, you multiply the second entries, you multiply the third entries, the fourth entries, finally to the last entries. I multiplied the first entries, the second entries, all the way up to the last entries. And you add them up. This is nothing more than, in sigma notation, AI times BI. After all, what doesn't change from each are A and B. A times B. A times B. That's why I have A times B. What does change? The subscripts. The subscripts. They're both the same, and they change. So I call them I. And I say I goes from 1 all the way up to N. It's the summation of AI, BI. Okay. That is the dot product. Nothing major. Multiply the 2 first entries plus multiply the second 2 entries, etc. So if A is 314 and B is 210, the dot product will naturally be 7. The dot product will be the number 7. A dot B. Why? Because 3 times 2 is 6, plus 1 times 1 is 1, and 6 plus 1 is 7, and 4 times 0 is 0. So you get 6 plus 1 plus 0, also known as 7. That's the dot product. The sizes have to be the same. If A has 3 entries, then B has to have 3 entries. Otherwise, like if A had a 4th entry, if the 4th entry was 7, what would you multiply this 7 by? Plus 7 times blank space? That is 7 times I don't know? Well, the answer would be I don't know. I don't know what 7 times I don't know is. Do you know? I hope not. In the 1 by n and the n by 1, for the dot product to be defined, the n's have to be the same. Do one more example, show you that it's really not a big deal to compute the dot product. In fact, it's quite simple. If A is equal to 3, negative 1, 2, 4, and B is negative 1, negative 2, 0, 5, then A dot B. You multiply the first entries, you get negative 3. Plus, you multiply the second entries, you get positive 2. Plus, you multiply the third entries, you get 0. You multiply the fourth entries, you get positive 20. That gives you negative 1 plus 0 is still negative 1. If you owe somebody $1 and you give them $20, you're ahead $19. It's not a big deal to compute the dot product. On to matrix multiplication. On to matrix multiplication. You have two matrices. You want to multiply them. If A is equal to 2, 1, 0, 3, 1, 4, and B is equal to 1, 1, 1, 0, 1, 2, 1, 1, 1. Okay. In general, let's see equal to A times B, which is not A dot B. Okay. The Cij entry will be the summation of A, Ik, Bk, J. And K goes from 1 to n, where n is the number of columns in A, which is the same as the number of rows in B. We'll talk about that. It's just the dot product. It is just the dot product. In fact, let's pause on doing this multiplication in a moment. If you have A11, A12, up to A1, up to A1n, and you have A21, A22, up to A2n, and eventually you get to the ith row. Ith row first column, ith row second column, all the way up to the ith row, the nth column. That is matrix A. And you want to multiply, all the way down to the nth row of matrix A, first column, nth row, second column, nth row, mth column. Well, let's say there's m columns. Okay. So that's matrix A. Now, matrix B, you're going to have the first row, the first column. You're going to have the first row, the second column. Eventually, you'll get to the first row, the jth column, all the way up to the first row, the mth column. You'll have the second row, first column, the second row, second column, the second row, jth column, all the way down to the second row, the nth column. And I think I've been saying n, at least I hope I have. Let me think. Yeah, these should be n. Actually, let's call it P. Now let's see if that, yeah, let's call it P. And then this keeps going all the way to the nth row. First column, nth row, second column, all the way up to the nth row, the jth column, and in the nth row, the pth column. Now, when you multiply these two, you're going to get another matrix. And the question is, what, and that matrix we call, say, C. A times B, the first matrix is A times B, and the matrix that we get, we're calling it C. What would the ith J entry be? Row I, column J. Right there. What goes there? Okay. I'm going to erase the top. Sorry about not writing in a better order, top to bottom. What is going to go in that ith jth position? And the answer is the dot product of row I of matrix A, of the left matrix, dotted with the jth column of the second matrix. Cij, the dot product. It's row I of matrix A dotted with column J of matrix B. Now let's see what it is. We multiply the first entries, AI1, B1J, plus we multiply the second entries, which is AI2, B2J, and we multiply the third entries, which would be AI3, B3J, all the way down to we multiply the last entries, AIM, BMJ. Okay, that will be the Cij entry. You get rid of a little bit more. That will be the Cij entry. The Ij entry of the product. But now, if we looked at this a little bit more carefully, since we're adding up lots of things, what you can think of is sigma notation. Now, what you need to do to decide how to write sigma notation, in my opinion, is very, very visual. What's the same in all of the sums? They both have an A and an I, and a B and a J. A and an I, B and the J. The A and the I, the B and the J. They all have that. A sub I, B, and then J. So it's A sub I, B, J. Now, what's changing? Well, first you have ones, and then you have twos in those locations, and then you have 3 in those locations, and then you have M in those locations. Well, normally I would sum over I, but I already have I. So let's call it K. Let's call these Ks. And K goes from 1 to M. But if you look at this, it's exactly this. So I'll even change that to M, the upper limit. It's just the dot product. You dot row, so you dot row I with row J, and you put that position in the row I, column J position in their result. Lots of words, I admit that, but let us do a couple of examples, and you'll see that it's just like the dot product that I did at the very beginning, except there's many of them. So when somebody asks you to multiply 2 matrices, they're just asking you to dot a lot of row vectors and column vectors. They're just asking you to do a few. 2, 1, 0, 1, 2, 4. Multiply this matrix with 1, 2, 3, 0, 1, 1, 1, 2, 1. Multiply this and put the result here. So I'm going to dot row 1 with column 1. Row 1 is 2, 1, 0. I'm going to dot this with 1, 2, 3. 2 plus 2 plus 0 is 4. That goes in row 1, column 1 position. Now I do row 1 with the second column, if in fact there is a second column. This is row 1, and I dot it with the second column, and I get 1. because 2 times 0 is 0. 1 times 1 is 1. And 0 times 1 is 0. And 0 plus 1 plus 0 is 1. Row 1, column 2, right here. Row 1, second column. Then I attempt to dot row 1 with column 3. And I can only succeed if there is a column 3. And there is 2, 1, 0, dotted with 1, 2, 1. Again, I think we're going to get 4. 2 times 1 is 2. 1 times 2 is 2. 2 plus 2 is 4. And then I add 0. Row 1, column 3. I put a 4. Then I attempt, let me just make this 4 clearer. Then I attempt to do row 1 with column 4 of the second matrix. But there is no fourth column. Okay, so I'm done with row 1. Now I do the same thing with row 2. I dot row 2 with column 1. I dot row 2 with column 2. And finally, row 2 with column 3. And I remember there is no column 4. Okay. Row 2 is 1, 2, 4. And I dot it with column 1. And here I'm going to get 15, I think. 1 plus 4 is 5. So I'm wrong, 5. 5 plus 12 is 17. Row 2, column 1. That's right there. Row 2, first column. Now I dot row 2 with column 2. Column 2 is 0, 1, 1. And I'm pretty sure we'll get 6. Just add those two numbers. 1 times 0 is 0. Why do I add the two numbers? Because I'm multiplying the numbers by 1. 2 times 1 is 2. 4 times 1 is 4. 2 plus 4 is 6. Row 2, column 2. I put a 6. Row 2, column 3. This is row 2, and this is column 3. I get 1 plus 4 is 5 plus 16. 5 plus 16 is 21. Put 21 here. And I am done with row 2. So then I attempt to multiply row 3 or dot row 3 with column 1. And I'm like, oh, it is no row 3. That's when we stop. That is the answer. That is the answer. Okay? You dot each and every row of the left matrix with each and every column of the second matrix, the right side matrix. And you put the results in the logical position. If you multiply or dot the second row with the third column, row 1, row 2, column 1, column 2, column 3. Second row, third column. When you dot row 2 with column 3, the rows come from the left matrix. Their columns are coming from the right-hand matrix, left matrix, right side matrix. The answer goes in row 2, column 3 position. It's just the dot product. That's all it is. Many of them. You know how on the bottom here we did 6 dot products. We did 6 dot products. Instead of writing out 6 separate dot products, like class, do this dot product right here, and class, do that dot product right there. They just say multiply these two matrices, which is code for compute these 6 dot products. That's all it is. is just code for, oh, compute these 6 dot products, please. That's all it is. Don't think of it as anything more than, oh, they're just asking me to compute a few dot products. Otherwise, you can make this quite complicated. It's just computing dot products. That is why, if it's taught correctly, and it's almost impossible, if it's taught correctly, the first thing an instructor is going to do is teach you the dot product. I think it would be very unusual, if not never have occurred ever, that you're not taught the dot product right before matrix multiplication, because that is all it is. Let's do another one. 1, 2, 3, 4, 1, 0, 1, 0. We'll multiply this by 2, 2, 0, 3, 1, 1, 1, 0. And multiply those two matrices. And when you multiply two matrices, you get a matrix. So, if they exist, I'm going to dot row 1 with column 1. And row 1 is 1, 2, 3, 4. Remember, the rows always come from the left side matrix, and the columns always come from the right side matrix. Times column 1. 2, 2, 0, 3. 1 times 1 is 2, plus 2 times 2 is 4, plus 3 times 0 is 0, plus 4 times 3 is 12. Looks to me like 18. So in row 1, column 1 position, I put the number 18. Then I attempt to do row 1 with column 2. I have row 1, but I don't know if the next matrix has a column 2. And yes, it does. 1, 1, 1, 0. So you just add the first 3 numbers, because 1 times 1 is that number. 2 times 1 is that number. 3 times 1 is that number. Those 3 numbers add up to 6. And then you add 0. You get 1 plus 2 plus 3 plus 0, which is 6. Row 1, column 2 position. Then you attempt to do row 1 with column 3. Well, the second matrix has first column. It has a second column. Doesn't have a third column. Okay? So then, just to save space, I'll erase that. So we're done with row 1. Now, you go on to row 2. And you dot it with column 1. Okay, if possible. There's a chance you can't dot row 2 with column 1. How can that possibly happen? And the answer is, what if there was no row 2? What if the left-hand matrix was just 1, 2, 3, 4? It doesn't have a second row. But that's not the case, hence we go on. We're going to dot row 2 with column number 1. Row 2 is 1, 0, 1, 0, and column 1 is still 2, 2, 0, 3. And here, we're going to get 2, because 1 times 2 is 2. And multiplying by those zeros aren't going to give anything, so we're down to that 1. But that's being multiplied by 0. We just got 2. 2 plus 0 plus 0 plus 0 is 2. Row 2, column 1. Now, try to sneak it in here. But now we're going to dot row 2 with column 2. This is row 2, and column 2 is that. And when we add these, we get 1 plus 0 plus 1 plus 0, which is 2 again. In the row 2, column 2 position, we put 2, 2. Well, we've already been through the fact that there's no column 3. So we did row 2 with column 1 and column 2. So we're done with row 2. Now we attempt to do row 3 with column 1 and column 2. But there is no row 3. So we stop. I'll put the bracket even a little bit closer, and we'll say we're done. We're done. Okay. So matrix multiplication is nothing more than dotting each row with each column. Almost like the FOIL method. Everything in the left bracket has to be multiplied with everything in the right side bracket. With matrices, the brackets are the matrices, the numbers in the matrices, and we don't multiply each entry, but rather, well, let me say it differently. When it comes to regular multiplication, we multiply each term in the left bracket by each term in the right-hand bracket. Okay, we distribute. Now, if you have x plus 3x squared plus 9q, and you're going to multiply this by 3y minus 2xy. The terms are separated by addition and subtraction symbols. The only thing I didn't underline were the term separators. And basically, you multiply the first term with the first term with the second term, and if there was a third term, you'd multiply the first term here with the third term. But there is none, so you stop with the first term, you're done. Now you do the second term with the first term, the second term with the second term. And you cannot do the second term with the third term because there is no third term. So then you move on to, if you have, the third term. So we're done with the second term. Now you go on to the third term. Multiply it by the first, multiply it by the second. And then you distribute the fourth term. Oh, there is no fourth term in the left bracket. With matrix multiplication, it's similar, except you dot rows with columns. You multiply or dot the first row with the first column, the first row with the second column, the first row with the third column, until you run out of columns. Then you do the second row, and you dot it with each of the columns. And then you do the third row, and you dot it with each of the columns. And you keep doing that until you run out of rows. Now, can you multiply these two matrices? 2, 1, 3, 1, 4, 0. You want to multiply this with 2, 3, 0, 1, 1, 2. Negative 2. Can you multiply these two matrices? That is, can you dot row 1 with column 1? Well, this is row 1. I'm going to dot it with column 1. And hopefully you see that there's a problem here. Sure, you can multiply the first entries. 2 times 2, 4. You can even multiply the second entries. But there's no third entry in the left matrix to dot with the third entry in the right matrix. This is not well defined. This is not well defined because the number of columns, column 1, column 2, does not match the number of rows in the second matrix. Row 1, row 2, row 3. Now, I think I got physically ill when my teacher did this because every time up to now when we were talking about matrix multiplication, the left matrix we always talked about rows. Take the first row, dot it with the first column. Take the second row from this matrix, dot it with column 3, etc. But now it reversed. Now my instructor started talking about columns in the left matrix. The number, when you want to dot rows 3, say with column 2, since this has 2 entries and this has 3 entries, there's a problem. Now, why does this have 2 entries? And you can't just say, well, I counted them. The answer is there's 2 columns. And why does column 2 have 3 entries? And the answer is there are 3 rows. The number of columns in the left matrix must equal to the number of rows in the right-hand matrix. The number of rows in the left-hand matrix, the number of columns in the left-hand matrix must equal the number of rows in the right-hand matrix. Now, it's not that bad. If the left-hand matrix is m by n, the right-hand matrix, well, let's go over this carefully. Rows, columns, rows, columns. The number of columns in the first matrix, which is that number, must equal to the number of rows in the second entry. The number of rows is that number. That is, these have to be the same. And it turns out, and we'll look at it carefully, it turns out that the columns in the second matrix can be any number. The first matrix can have any number of rows, and the second matrix can have any number of columns. But those inner numbers, notice I'm not even saying columns and rows anymore. The inner numbers have to be the same. The inner numbers have to be the same. And it turns out that the size to be well defined, if the inner numbers are not the same, you can't do the matrix multiplication. It turns out that the outer numbers, m by q, will be the size of the product. The inner numbers have to be the same, and if they're not, you can't do the multiplication. And if they are the same, then the matrix will be m by q. The matrix will be m by q. So for 2 matrices, for multiplication of 2 matrices to be well defined, it must be that their inner numbers are equal to one another. The number of columns in the left-hand matrix must equal to the number of columns, in that right-hand matrix. And if that's the case, then the matrix is very well defined. Now, let us look at this a bit more closely. Suppose A is m by n, and B is n by q. Okay, so let's look at A. It has n columns. So the first row will be A11, A12, up to A1n. The second row, first column, second row, second column, all the way up to the second row, the nth column. The matrix A has m rows. So eventually, we'll get to that last row. Row m, first column, row m, second column, up to row m, nth column. And we're going to multiply matrix B. So let me in front write AB equals. Now, matrix B has q columns. So you have first row, first column, first row, second column, all the way up to the first row, the Q's column. And then you have the second row, first column, the second row, second column, all the way down to the second row, Q's column. But matrix B only has n rows. So eventually, you'll get to the nth row, first position, nth row, second position or second column, nth row, the Q's column. Now, if we were to multiply this, I just want to know the size. How many columns? Like, you can multiply row 1 with column 1. Well, that will go here. Row 1, column 1. And then you can dot. I meant to say dot. First I dotted row 1 with column 1. Then I'll dot row 1 with column 2. And that will go right here. Row 1, column 2. And eventually I'll dot row 1 with column Q. So I'll have column Q. And then I'll go on to row 2. I'll dot row 2 with column 1. That goes right there. Row 2, column 1. And then I'll dot row 2 with column 2. It goes there, etc. Then eventually I'll get to there. I'll dot row 2 with column Q. That brings me there. And I dot the third row with the first column, the third row with the second column, all the way down to the third row with the Q's column. And then eventually I'll get to the nth row, dot, 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 row M. And I'll dot row M with the first column, and I'll dot row M with the second column, all the way up to row M with the Q's column. Well, let's see. This is a blank by blank matrix. What are the blanks? How many rows does it have? Row 1, row 2, row 3. Oh, it has M rows. How many columns does it have? Column 1, column 2, column 3, column 4, all the way up to column Q. Okay, so what I said earlier, and I want to look at that once again. What I said earlier is absolutely true. If I take an m by n matrix, which is size A, which is matrix A, and I multiply it by an n by q matrix, those are the same, which is good. So my result should be, or I claim my results is n by q. Yep, I'm right, because the bottom one, this one, we know is correct. We actually multiplied it out. Up here, I just said it. I just said it's m by q. Did I justify it up there? No. But I certainly did down here. I actually went through as if I multiplied the two matrices. You know, I just talked about where I would put the results. But I don't need to know the results to know the size of the matrix. This matrix has m rows on the bottom left. It has m rows and q columns. Okay. So, matrix multiplication is not always well defined. Sometimes it is, other times it isn't. Now, here's something that's very interesting. Does A times B have to equal to B times A? That is, does matrix multiplication have the commutative property? And if you just think about sizes, the answer is no. The answer is no. And we'll talk about why the answer is no in a moment. and we'll just talk about sizes. Suppose A is 3 by 4, and matrix B is 4 by 5. Okay? So what will AB equal? Sorry, what will the size of AB be? Well, it's 3 by 4 by 4 by 5. And you say, yes, you can multiply A and B because those two numbers are the same. And the answer to the size question will be the outer number. A times B is 3 by 5. Okay? Now, if BA is 3 by 5, then I'm not going to say they're equal. Not all matrices, not all 3 by 5 matrices are exactly the same size. But if it's not even a 3 by 5, then forget about it. It can't be, the two matrices can't be equal. That's the size of B. This is the size of A. Those are not equal. B times A is not well defined. A times B is a 3 by 5 matrix. B times A isn't even well defined. AB does not equal to BA. Suppose C is 3 by 4 and D is 4 by 3. Well, C times B, at least size-wise, will be 3 by 4 by 4 by 3. Those numbers are the same size. So we're going to get an answer. The answer is 3 by 3. Okay. CD is a 3 by 3 matrix. What is DA going to be? Well, D is a 4 by 3, and A is a 3 by 4. And those numbers are the same, so we're looking good. We're going to get an answer, and the answer is going to be 4 by 4. Well, no 3 by 3 matrix can ever equal a 4 by 4 matrix. So here, DA does not equal. Okay, this is just a typo up here. I'm sorry. It should be DC. And I did put down the size of D, and I did put down the size of C. Okay, CD does not equal to DC. Now you may say, well, okay, they're only equal when they're the same sizes. A times B, if AB and BA are the same size, then they're going to be equal to one another. Is that true or not? Again, the only hope for them to be equal is if they at least have the same size. So what we're going to do is we're going to see what's the necessary conditions on the sizes for AB and BA to have the same size. And then I will show you that even then they don't have to be equal. But what's the necessary condition for them to have the same size? Okay. So we have an m by n, and we multiply by an n by p. I wanted it to be well defined. This is an n by n matrix. But what if I reverse them? What if I have the second matrix first? I have n times n by p, and I want to multiply this by n by n. I just switched the side. I switched the order that I'm multiplying. Well, now, we want this to be the same size, n by n. Okay. The first thing is p must equal to m. Okay? That's the first thing. Oh, excuse me. This is wrong. since the inner numbers were the same, we're going to get m by p. M by p. Okay? So we want the same answer here. We want this to be m by p. Now, here's the situation. P and m must be equal. Okay? Now, we get n by n. But again, but want m by p. That is m by m. Why m by m? Because p is m. That is n and m are equal to one another. Hence, n equals m, but m equals p. That is, all of these letters, m, n, and p, are equal to one another. If you understood that, wonderful. But I'm telling you, for the sizes to be the same, AB and BA, it has to be a square matrix. If one matrix is n by n, and the other matrix is n by n, you'll get an n by n matrix. Now, if I switch them, that is, this is A and this is B, and now I put B times A, well, B is also n by n, and A is also n by n. And we'll get n by n. They'll be equal sizes. The only time AB and BA will be the same sizes is if A and B are square matrices of the same size. A cannot be 3 by 3 and B be 2 by 2. Can they be equal? A, B, and BA? The answer is yes. Will they always be equal? If A and B are square matrices of the same size? Absolutely not. Let A equal to 1, 0, 0, 1, and B equal to the square matrix, 2, 3, 1, 5. Well, what is AB? Well, it's 1, 0, 0, 1 times 2, 3, 1, 5. If you dot the first row with the first column, you just get the number 2. 1 times 2 plus 0 times 1. If you dot the first row with the second column, you'll just get 3. 1 times 3 is 3, plus 0 times 5 is 0. 3 plus 0, 3. Second row with the first column. 0 times 2 plus 1 times 1 is 1. Second row, second column. You just get a 5. And if you suffer through this multiplication, you suffer through this one, work it out, you see you get the same answer. So in fact, given the A and the B on the top, AB equals BA. But this is not always true. I'm hoping this example will show it. A and B is, let me stay away from zeros, 8, 2, 1, 4. Well, AB, 1, 2, 3, 4, multiplied by 8, 2, 1, 4. First row, first column. 8 plus 2. 1 times 8 is 8. 2 times 1 is 2. That gives me a 10. First row, second column. You get 2 plus 8, which is also 10. Okay. Second row, first column. 3 times 8 is 24, plus 4 ones bring you up to 28. 6 plus 16. 3 times 2 is 6, plus 4 times 4 is 16. That's AB. Now, what is BA going to be? Well, this is matrix B, and I multiply it by matrix A. Do the first dot the first row with the first column. 8 times 1 is 8. 2 times 3 is 6. 8 and 6 is 14. First row with the second column. Get 16 plus 8. 24. Now you can say already they're not equal because 10 doesn't equal 14. Second row was the first column. 1 plus 12. 2 plus 16. Okay, so I computed AB and I computed BA and I say, oh, AB is not equal to BA. And for the record, they're both the same size. They're both the same size. They're both 2 by 2s. They could have both been 5 by 5s, and AB does not equal BA. But in this case, they're 2 by 2s. So it is not always the case where AB and BA are equal. The only prayer for them to be equal is if they're both the same size. And even then, you have to do the computation. It turns out that AB and BA were equal here. But AB and BA down here were not equal. And they were both the same size. Okay, so now we get into more fun stuff. This is the start of why we're learning anything about matrices. Okay, matrices, they're very powerful. Linear algebra, learn a lot of theory, but you can actually apply this stuff if that's what you're into. Personally, I think that gets in the way. Suppose you have this linear system. Negative 3x plus no y's plus z. Let it equal negative 1. Doesn't matter. 2x minus 3y plus z. This time let it equal to 4. 3x plus 2y plus 3z is equal to 9. All right. First thing I want to emphasize is there is an understood plus 0y, and those are 1z's. Well, suppose I let A, matrix A, just be what's called a coefficient matrix. That is, the numbers in front of x, the numbers, including the signs, in front of y. Of course, the positive signs you don't have to write, followed by the numbers in front of z. 1, 1, 3. And we'll let, so here's a case where we're not using a capital letter from the beginning of the alphabet. How about we let capital X equal little x, little y, little z. For the record, little x, little y, little z. And let little b, first time we ever used a little letter. Now, let me just say it again. If you have a column vector, you can call it x. It's generally, you can call it capital A or capital B, but generally we call it capital letters from the end of the alphabet. Capital X, capital Y, capital Z. And little b is also going to be a column vector, but it's going to be the numbers on the right-hand side of the equal sign. That's little b. Okay. Now, let's look at A times X equal B. That is negative 3, 0, 1, 2, negative 3, 1, 3, 2, 3. That's A. And let's multiply it by x. X, y, z. Okay, well, just for the record, A is a 3 by 3 matrix, and B is a 3 by 1 matrix, and the inner numbers are the same, so we're going to get back a 3 by 1 matrix. 3 rows, 1 column. Get negative 3 times x plus the 0 times the y plus the 1 times the z. For the second row, you get negative 2 times x, negative 3 times y, and finally 1 times z, which I'll just write as z. For the last row, you get 3 times the first entry, 3 times x, 2 times y, plus 2 times y, doing the dot product, plus 3 times z. That's A times x. And yes, it does equal to B. It does equal negative 149. That is, this does equal negative 1. Look at the very top line. And yes, this second row does equal to 4. Look at the second equation. Likely, the third row equals 9. Okay, so you can take this. You can take this and write it in AX equal B form. A is just the coefficient matrix. If you need to insert zeros and ones, go for it. Okay, you take the coefficient matrix, 3, 2, 3. You multiply it, in this case, by the variables x, y, and z, and you get the numbers on the right-hand side. This equation, it's an equation because it has an equal sign, is the same as those 3 equations on top. It's a shorthand notation. It's shorthand notation for the same exact thing. Let's look at another example like this. You must be able to go from a high school algebra written system of equations and translate it to matrices. You just have to be able to do that. So if you have 2x plus 3y minus 2z is 11, and 4x minus 3y equals 12, and you have 2y equals to 16. The first thing, and the problem is, or the question is to write this in AX equals B form. The first thing you need to do is realize that adding 0z, which is 0, you can do. You can add 0. And after all, 0x is 0. And when you add 2y to that, you just get 2y. And then if you add 0z, you have 0 plus 2y plus 0, which is 2y. Exactly what we had before I put what's in the red. A x equals b. Well, the A will be 240, the numbers in front of x. The y's will be, the second column will be the numbers in front of y. 3, negative 3, 2. And then negative 2, 0, 0. The numbers in front of z. And the variables in this case, in order, are x, y, z. So I write x, y, z. And it equals to the right-hand numbers. But you really, really need to convince yourself. Just by multiplying this out, just take the first row, dot it with the first column. Take the second row, dot it with the second, with the first column, the only column. Take the third row, dot it with the first column, and see what you get. And what you should get is exactly this. And here, that equals 11, 12, 16. You need to be able to go from the top 3 equations to this matrix equation here. And then even a little bit more. Not a big change. I'm going to write down just the coefficient matrix. I'm going to write down the coefficient matrix. There it is. But I'm not going to write x, y, z. I'm going to put a line. My daughter's in first grade and they taught her how to write a 1. Put a dot and go straight down. Okay? And she tells me I understand math. Math is fun. I know how to write a 1. Actually, she learned that in kindergarten, excuse me. So just go, draw a straight line, and then put down the right-hand side numbers. Okay? Just put down the right-hand side numbers. This is called, I'm going to write it here because I want space on the left. This is called an augmented matrix. How do you know it's augmented? Very, very simple. It has that line. You see a line, you say, oh, that's an augmented matrix. Okay, you see any of your teachers, they wrote that in their blackboard in their office, and you want to sound smart. You say, oh, I see. Once you see this, you go, oh, that's an augmented matrix. I understand what you're doing on the board. Probably have no idea what they're doing, but it's an augmented matrix. Absolutely correct. So if you have 3x minus 2y plus z equals 11, it's understood to be 1z. 2x plus 3y minus 2z is 13. 1x plus 1y plus z equals 2. An augmented matrix is, well, remember you have 1s here. Just write down the numbers in front of x. Put zeros in if you need to. The numbers in front of y. Negative 2, 3, and 1. The numbers in front of the z's. 1, negative 2, 1. Then put your augmented line. And then write down the right-hand numbers. And you translated this system of equations into an augmented matrix. There is nothing to it. Nothing. You need to be able to go from a matrix to augmented matrix and, from a system of equations to an augmented matrix, and a system of equations to AX equals B format. AX equals B. Now, I'm not the one who named these things. This matrix X is not that number X. Okay? Matrix X is equals to, say, X, Y, Z. That X and that X are different. That X right there is a real number, like 2. And the Y is negative 3, and the Z is the number pi. X, little x, Y, and Z are real numbers. This big capital X is a column matrix. a column matrix cannot equal to a number. Okay, unless the column matrix just has one number in it. But still, I won't say it equals a number. In this example, the column matrix X is equal to the column matrix where the one column is just 2. Here, the matrix X is a column vector where the entries are 2, -3. So you'll see X's in 2 places, but they have different meanings. Absolutely different meanings. Okay, on to the theoretical exercises. Okay. Let X be a 1 by n matrix. Now, once one of their dimensions, row or columns, is 1, you know it's either a row or a column matrix. Since the row, remember, it's always row by columns. Since the row is 1, it is let X be a n by n row matrix. Now, the first question, there'll be 2 parts to this. Is it possible for X dot X transpose to be negative? Is it possible that X dot X transpose be negative? Let me erase it a little better. Should be negative. And I hope you see that the answer is no. Okay? No. Here's my solution. No. But you just can't say yes or no. You have to explain it. Let X equal A1, A2. They said it has n columns, so I'll put n columns. So what will X times X transpose, X dotted with X transpose be? Okay, well, we know what X is. A1, A2, up to AN. Dotted with the transpose. Well, the first row I write as, for the transpose, I write as the first column. And that's it. There is no second row of matrix X to write as a column, to write as the second column of X transpose. So I get A1 squared, because A1 times A1 is A1 squared, plus I get A2 times A2, which is A2 squared, plus A3 times A3, all the way up to AN times AN. Now, what type of objects are A1 and A2 up to AN? Even if I look here, what type of objects are they? And the answer is they're real numbers. I mean, X could have been 3, 1, 4, and then, or 3, 1, negative 4. And I dotted with the transpose. The and let me sneak in a 0. 3, 0, 1, 4. So let me write it a little bit bigger. The bottom line is each of those numbers just get squared. And when you square numbers, you either get 0 or above. 3, 0, 1, 4. If I dot this with the transpose, I get 3 squared, which will not be negative, 0 squared, which is 0, 1 squared, which is 1, and let's make the 4 as negative. Negative 4 squared is 16. 15 14, and 9 is 24, plus 0 is 24. It's not going to be negative. This here is greater than or equal to 0 since each xi is greater than or equal to 0. That's greater than or equal to 0 since ai is 0 or more, and this is for all i's, 1, 2, up to n. For I equal 1, 2, up to n. Okay, so it's always positive. It's always positive. Keeping the same premise, that is, well, keeping the top line, x be a 1 by n row matrix, what must be true if x times x transpose equals 0? And what can you say about x, matrix x, if x times x transpose equals 0? If x times x transpose is equal to 0, no, it equals to 0. Because when you dot when you dot a row matrix with a column matrix, you get a real number. If x dot x transpose equals 0, then what can x be? Okay, solution. We'll find out at the end. Let x equal a1, a2, up to an. And on one hand, x times x transpose, we just worked it out, is a1 squared plus a2 squared all the way up to an squared. And they're telling us that it equals 0. Well, this implies that a1 equals a2 all the way up to an are all zeros. That is, each of these are zeros. Because if a1 was anything but 0, negative 4, 11, when you square it, it'll be more than 0. Each of these are 0 or more. Each of those is 0 or more. Well, once one of them is more than 0, when you add them up, you ain't getting 0. Okay. Well, if a1, a2 up to an is 0, that implies x is equal to a1, a2, a3, up to a0. X is the 0 row vector. Okay. The next one is a bit deeper. Show that the product of two diagonal matrices is diagonal. Show that the product of two diagonal matrices is diagonal. If you multiply two diagonal matrices, you get a diagonal matrix. Okay. So let's formally state it. Show that the product of two diagonal matrices is a diagonal matrix. Of course, it's built in that the two diagonal matrices are of the same size. A proof. Let A and B be two m by m diagonal matrices. Now, remember, a diagonal matrix has zeros off the diagonal. It can have whatever on the diagonal. A is the square matrix, and B, it has zeros off the diagonal. So, Aij is, well, sometimes you just get Aij. But sometimes you know what Aij is. It's 0. It's 0 every time I and j are different from one another. And you just get Aij if you're on the diagonal. If you're off the diagonal, you can tell me what Aij is. That is, what is A23 on a diagonal matrix? Even if I didn't give you the matrix, you say it's 0. It's off the diagonal. If I ask you what A33 is, you can only say, well, it's A33. I don't know what it is. But if it's off the diagonal, if you said A42, the 4 and the 2 are not equal. Oh, it's 0. We're assuming that the entry exists, okay? Matrix A has at least 4 rows and 4 columns. Bij is going to be defined almost the same. Sometimes you don't know what it is, so we'll just call it Bij. But sometimes you know what Bij is. Sometimes it's 0. In fact, it's 0 if I and j are different. And if I and j are not different, you really can't say what it is. It's just whatever Bij is. Oops. Okay, let's get rid of this on the bottom. So, how about we make the oops, what's going on here? How about we make the statement that C is AB? C equals AB. Let C equal to AB. So, what I want to show is if I equals J, oops, I have this backwards over here. Sorry about that. You get Bij when you're on the diagonal. That is, you don't know what it is. But if I is not j, then Bij is 0. Okay, so we want to say if I is not j, I want to see what Cij equals. Okay? What if I is not j? Now, we'll do that in 2 cases. Either I is not j for one of 2 reasons. Remember, I and j are just real numbers. Either I is less than j, or I is bigger than j. Suppose I is less than j. Okay? Suppose I is less than j. Well, you know what? Just to make life easier for me, let's suppose I is bigger than j. Okay, so now Cij, by definition, is the summation of Aik, Bkj, as k goes from 1 up to, well, matrix A has, has n m columns, and for the record, matrix B has m rows. So k goes from 1 to m. Okay. Now, we know that I is bigger than j. Okay? So what we're going to do is we're going to stop off. So k eventually will be I. K eventually will be I. I mean, k goes from the first 1 to m, which is all the rows, all the column values. I mean, if we're talking about row I, I can't be more than m. I mean, A has m rows. You have the first row, the second row, up to the mth row. One of those rows is I. So I can stop k right before I. I can just go up to I minus 1. aik, bkj. And then I can pick up for the next value of k. 1, 2, 3 up to I minus 1. The next value of k would be I. I'll go all the way up to m. So basically, here's 1 and 2 and 3, and here's I, and eventually here's m. And right before is I minus 1. So first k is 1, and then 2, and then 3, and 4, and 5, up to I minus 1. That took care of this. And now I'm going to let k go from 1 to m. Sorry, I to m. I plus 1, I plus 2, up to m. That is, I'm really summing from 1 to m by doing this addition. I'm just breaking them up. Okay. Now, aik ai anything is equal to 0 if these two values are different. Well, then this is 0. Why? Those two values are different. K can only be 1 or 2 up to I minus 1. K can never be I. The only value for K that will make aik not 0 would be aii, which is, well, which doesn't have to be 0. But the bottom line is, it's not equal to that, because k is less than I. K only goes up to I minus 1. And I don't care what bkj is, because 0 times anything is 0. So over here, we have 0 times bkj. So what we're doing is, which is 0. 0 times bkj is 0. And we're adding up zeros as k goes from 1 to I minus 1. That is, we have 0 plus 0 plus 0 a number of times. That's going to be 0. K plus. Okay. Now, we know that I is bigger than k. I is bigger than k. Sorry. I is bigger than j. We know that I is bigger than j. Okay? But k and anything bigger than I is bigger than j. But k is bigger than or equal to I. K is I, and then more than I plus 1, I plus 2, all the way up to m. And for example, if I was 7 to 12, m is 12. So that's I. Well, k is either that number, or k is 8 or 9 or 10. It's bigger. So if k is bigger than or equal to I, but I is bigger than j, that means k is bigger than j. K is bigger than j. This is always 0. Because if these are different, and if k is bigger than j, how is k going to equal j? If these are different, if k and j are different, we get 0. And I don't even care what aik is. Sometimes it can be not 0. I mean, after all, when k is I, then these subscripts are equal, and you get what's on the diagonal. It doesn't have to be 0. But nonetheless, aik times 0 is 0. So we're summing up zeros a lot of times. I to m times, which is 0 plus 0, which equals 0. So the next line you should write is, so what we showed is if I is bigger than j, so we're assuming this. We are assuming I is bigger than k. So now you can say, so by definition, C is a diagonal matrix. Why is that? Because Cij is equal to 0 if I is bigger than j. Okay. Now, what if I is less than j? What if I is less than j? That is, this time, j is bigger. J is bigger than I. Well, the only thing you should do different is play the same game with j now. Let k go from 1 to j minus 1. Don't start off at I. Start off at j. Start off at j. Okay? What might change is what's on top here. We have to think about that. Okay. In this first one, we know that j is bigger than I. But k goes up to I minus 1, j minus 1. K goes up to j minus 1. Well, let's just stop for a moment. Let's scratch that last comment. These two values will never be the same because k doesn't equal j. K is less than j. Because you have 1, 2, 3, up to k minus 1. Sorry, j minus 1. Those are the values that k can be. The next number is j itself. These are all less than j. Okay, k and j are never equal to one another. Hence, bkj is 0. And aik times 0 is 0. Okay, now let's come to the other one. We know that I is less than j. Okay? But j is less than or equal to k, because k can be j all the way up to m. In particular, I is less than k. I is less than k. Well, if I is less than k, then those two can never be the same. And if the subscripts are not the same, you get 0. And 0 times bkj is 0. So when you add them up, you get 0. And the only thing that should be changed here is the i's became j. J minus 1, k starts at j. All right. So we took care of when I is less than j and when j is less than I. That means I and j are not the same. Combining, we get Cij is equal to 0 if I is not j. By definition, C is a diagonal matrix, and I do want to say one thing. I should not have said that here. I want to remove it. I could have said it. So first we assume that I was bigger, then I was bigger than J, I is less than J. Combining that means I is not J. And in both cases, we found out that Cij was 0. If I is bigger than J, we get 0. If I is less than J, we get 0. You may say, but wait a minute. You didn't do the case when I is J. We don't care what you get when the subscripts are the same. For diagonal matrix, you must get 0. To show that a matrix is diagonal, you must show that when you're off the diagonal, you get 0. You don't care what you get when you're on the diagonal. You don't care. It doesn't matter what you get when you're on the diagonal. Okay. Now, we talked before about matrices being commutative or not. That is, does AB equal BA? Well, here's this theorem that gives us a whole host of matrices where A times B will equal B times A. Let A and B be two n by n diagonal matrices. Show that A times B does equal to B times A. That is, if you just take two diagonal matrices of the same size, they'll commute. Are they the only ones? No. No. I truly don't believe that. Now, letter C, in a numerical example, does this work? 3, 0, 0, 1. The first row dotted with the first column. Basically, you're just multiplying the 2 and the 3 to get 6, because 0 times 0 is 0. And then with the second one, the 2 gets multiplied by the 0, which is 0. The 0 gets multiplied by the 1. That's always going to be 0 here, even if there weren't 2 and 3. The second row was the first column. This has to be a 0, and it gets multiplied coincidentally by 3. And when you multiply the second entries, this has to be a 0, which is being multiplied by 12. The bottom line is you get 0. Likewise, when you multiply the 0, 12, dotted with the 0, 1, that is the second row, first column, this 0 is designed. And whatever this number is, it gets multiplied by that number. Now, if I reverse the matrices, the same things are going to happen. The same thing's going to happen. 2 times 3 is 6, but then you multiply zeros. Now you dot the first row with the second column. And by design, it's going to be 0. There must be a 0 here. 3 times the 0 is 0. And there must be a 0 here. And 0 times 12 is 0. Now, the second row with the first column. There must be a 0 here. So when you multiply it by that number, you get 0. And there must be a 0 here, because it's off the diagonal. When you multiply the 1 by that, you're going to get 0. And since I wrote on it so much, I'm going to put here the second row with the second column. This will be 0. And you'll always be multiplying the number in this position with the number in that position. And if you look, they really are equal to one another. So there's a whole host of situations, or one situation, that yield an awful lot of matrices that commute. So what we need to do is not show one example. Possibly those two diagonal matrices, they commuted. AB equals BA. But possibly with other two, they won't commute. Possibly with other two matrices, they won't commute. That is, we need to prove this in general. Let A and B be any two general n by n diagonal matrices. You can't plug in numbers. The only time you can plug in numbers is to disprove this. Show or disprove that AB equals BA. And you say, look, here are two diagonal matrices. AB give us this, BA give us that, and this and that are different. And you can plug in numbers for A and B. But here, it is valid. It is valid. You're not going to come up with a counterexample. Okay, so proof. Let A and B be two n by n diagonal matrices. M for matrices. So Aij is going to equal to, sometimes you don't know what Aij is, other times you do. You get Aij if I and j, you get 0, if I and j are different. And if I does equal j, you really can't say what it is. In other words, A23, since I and j are different, I get 0. A44, since I and the j are equal, I can't say what it is. It's just A44. But if I and j are different, I know what it is. I know what it is. Okay. Bij, pretty much the same. Sometimes you know what it is. Sometimes you don't know what it is. If I is j, if I equals j, you don't know what Bij is. But if I is not j, you surely should know what Bij is. It's 0. And this is only if B is a diagonal matrix, and we were given that. Okay. So now, we already showed, so let's take that. We already showed that when you multiply two diagonal matrices, we already showed that AB and hence BA, because B and A are two diagonal matrices, we already showed that AB is a diagonal matrix. Okay? So we know they're diagonal matrices. Okay? That is, we know that off the diagonal, we're going to get 0. That is, I don't know how I'm going to write this, but off the diagonal, I forgot the A, excuse me, they're equal. Off the diagonal, they're equal. In other words, AB might be 1 or 4005, and BA might be 7004. Okay? And if I put 2 dots above it, that means the equals only means off the diagonal. Notice, everything off the diagonal are equal. That is, what I need to show is that everything on the diagonal are the same. That is, that 7 is really a 4, and that 4 is really a 5, just like over here. I just have to show that what's on the diagonal are the same. Okay, so let me just formally write that off the diagonal, they're equal. Okay. Since AB and BA are diagonal matrices if I is not equal to J. Let's call this C, and let's call that matrix B. Okay, hence, because of the last line, if I is not equal to J, Cij does equal to Dij, which are zeros, okay? So I need to show what's on the diagonal are equal. Let's see what is on the diagonals for C and D. Okay. So, I is equal to J. What is CII? What is CII? Well, it's the summation of AIK, BKI, as K goes from 1 to M. But now, most times, this is 0, except when K is I. In fact, most times, that's 0, except when K is I. So this is nothing more than AII, BII. Now we can continue here, and conclude what we want, but let's slow it down. Let's do it in 2 steps. What is BII? Well, that's B times A. That's B times A. This is the summation of BIK, AKI, as K goes from 1 to N. It should be N on the top, sorry. Because I said that A and B are N by N matrices. Well, most times this is 0, except when the subscripts are the same. And that happens when K is I. Same argument here. Only when K and I are the same might we not get zeros. So the only time this might not be 0 times 0 is only when K is I. That is BII, AII. But these are real numbers. Real numbers commute. Real numbers commute, and you say equal. That is, when I and J are the same, Cij, or if you prefer CII, and Dij or Dii are equal. What's on the diagonal is equal. We just get them by commuting the numbers we multiply. When you do A times B, you might be multiplying 2 times 3 to get their 3, 3 position. But B times A, you'll be multiplying 3 by times 2. The numbers just switch order. So here, they're equal. Okay, so now you can say AB equals BA. They're equal off the diagonal. There are always zeros off the diagonal, and the Cij and the Dij are equal to one another off the diagonal, and when they're on the diagonal, equal. So they're equal everywhere. On the diagonal, off the diagonal, AB equals BA. Okay, that completes the video on dot products and matrix multiplication. Study hard, folks.